Hello. I want to talk about surface area. So here I want to compare two methods that we generally use to calculate surface area. The length times breadth of a rectangle, and that we've generalized into calculus, and in calculus and we use to calculate we can use that for area of any solid of revolution. So, and then the more general one, which is the cross product of two vectors. So here you can use that to calculate the area of a triangle that they enclose. So even though we learned that in 2D, it applies to three dimensions. So what I want to do here is to generate a figure and then try to see if calculating the surface area of that figure from the two methods give the same area. So people have talked about volume revolution, and then it's difficult for some people to actually see how some objects are classified as volume revolution, something like a cylinder or a sphere or a paraboloid. I think a paraboloid is simple. So let us talk about a paraboloid. So here I'm going to a parabola is actually a parabola that we rotated about one axis, like its principal axis to create a 3D surface. So let's see how it looks like. This is a nice shape. All right, so let us put a new section and then do the revolution about the z axis. So in that case, I'm going to convert my y to z. So z equals y and y equals 0. All right, so this is just one small strip of a paraboloid. So let us do the rotation around and then see how it looks like. So let's see. So we go. Okay, so let's see. So that is the surface of revolution. So now there are two ways to calculate the area. So let us see. So how do we calculate the area of this? So that there is one way where we divide the surface into different rectangles and then divide the rectangles into triangles and then we compute the area. So how do we compute the area? In that case, so we are going to just be making vectors from the point. So I've created a function for that. This is the surface area of any object at all, as long as you have the surface handle. So just send the surface handle. It will go inside and extract the coordinates and then make the vector surrounding any triangle from the rectangles and then compute the area and then accumulate all the area. So, but that's not the one I want to talk about now. So, because that one is easy, so let us talk about the one that requires calculus. So that's it. And then we can add a section break just to isolate this area. And then let us write the code for that. So to do that, so that is area. So by integration integral. And then we can have here times 5. Oh, sorry, 5 or 2. 10 times. So Here we have y, then y plus 1. So our integration goes from 0 to 2. So because y goes from 0 to 2, so y is 0 when x is 0 and it is 2 when x is 1. So the revolution goes about that way. So we can evaluate this and then see what the result is. So let us just run this section. Okay, now this is the result. All right, so if we send this guy right here into the code that I wrote to calculate surface area using the cross product vector. So let us see what that approximation returns. So let's see, we call that b equals, and then I'm going to bring this guy surface area of the soft handle. Then I'm going to pass s, which is the soft that we have. So let us run that and see what the result is. Okay, so they are close, not exactly the same. So the approximation is 9.0266. So let's see something because this one is almost exact. It uses calculus, and then this one is an approximation. So let us see if we can get this guy to be a little closer to this by just increasing the reducing the size of each triangle. That is by increasing the number of divisions. So here we go x to 21. So we use x to 1. We use 20 discretization. So let us make that, let's say, 100. So 101. And then here, let us go 100 also. That'll be 100. And then we need 200 of sub 100 to get to 2 pi. So I'm just going to be 200. All right. So let's see what the result is. It's close. It's still not exact. So what you have by calculus 9.0442, and then by approximation using vector cross product, we have 9.0435. And that's it. Thank you for listening.